when you're doing related rate problems, these are the steps you want to follow. They've got different steps, but these are the ones I like. The first thing you do is you read the problem, but that's just a given. Then you draw a picture or some kind of sketch so you get an idea of what is changing and how they're related to each other. Then you write down all the information that you know, and then you write down all the information that you're looking for, and then you write an equation. In this part, you're gonna look for different kinds of equations that you know apply to the problem. So if you look like, after you drew your picture, it looks like a triangle, and it's got to do with a ladder on a wall sliding, or something with a triangle on a wall. You're starting to think, okay, Pythagorean theorem. You might have a cylinder. If they give you it's a cylinder, you want to go back to your geometry formulas. It could be a sphere, or it could be any kind of thing where something is going to change in using that formula. There's also similar triangles, which we're probably going to use today. And other, those four are some of the formulas that you'll come up with, but they might give you the formula in the question. Okay, in the first problem, it says a balloon is being blown up at a constant rate. And let's just say the balloon is going to be a perfect sphere. The volume of the sphere is increasing at a rate of 100 cubic centimeters per second. How fast is the radius increasing? So what we have here is this relationship between the volume, or how the rate of the volume increases and how it's going to be related to how the rate of the radius increases, and they're related. Because as the volume of the sphere gets bigger, then the radius of the sphere gets bigger. And also, as the radius of the sphere gets bigger, then the volume of the sphere gets bigger. So you keep this in mind, and you say, all right, well, let's look at my steps of things that I have to do. So step one is draw a picture or a sketch. So I'm just going to draw something to give me some kind of idea of what's happening. And I know I've got this balloon, and as the radius is increasing, the volume's increasing, and also as the volume's increasing, the radius is increasing. So you've got this radius, and we'll call that R. And we know that we're dealing with volume. So the next step says write down the known information. Well, I know that it's increasing, so I know it's going to be positive, and I know that that's dV dt. That's going to be your increase. Your change is going to be positive. So dV dt is equal to 100 centimeters cubed per second. I also know that the volume of a sphere is equal to 4/3 pi r cubed. And they're asking how fast is the radius increasing, and I'm also going to add to this, what is it increasing? What is it increasing? What rate? Is it increasing when the radius is 25? And we'll get to that. Is it increasing when radius is 25? Centimeters, but I'll add that. Okay, so we're going to go ahead and use this formula. Now, I know that I'm going to differentiate with respect to t. So because there's a function inside of a function here, I'm going to have to use the chain rule. So I'm going to go ahead and say dv dt is going to be the derivative dr of 4/3 pi r cubed and then dr dt. And this is going to be the unknown that we're going to be solving for. That's going to be what we're looking for because it says how fast is the radius. And I probably should have put that in step number 3, write down what we're looking for. And we're looking for the change of the radius with respect to time. So let's go ahead and differentiate. Let me make some room. And when I differentiate this, I'm going to get, we'll write it again. It was dv dt is equal to ddr of 4/3 pi r cubed dr dt because it's implicit differentiation. So this is all part of the chain rule right here. So that's going to give me, I'm going to go ahead and take this, and that's going to give me 4 pi. I'm going to differentiate this part, the innermost part. And then I'm going to be left with dr dt. So make sure you know how I got that. The 4/3, you're going to go ahead and multiply that times 3. They cancel, minus 1, and that gives me the 2. So that's going to give me 4 pi r squared dr dt. And that's so far, we're at dv dt is equal to this. But I want to get this alone. So to get this alone, I got to divide by this part right here. So I'll end up getting dr dt is equal to dv dt times, and I'm going to divide it, right? So that's going to be 1/4 pi r squared. Now let me make some moves real fast so that we have some room. Okay, so I made some room so we can finish this. Make sure we keep our steps. And all right, so now from here, we found the rate is, or we were given dv dt. So we were given this right here. So let's just go ahead and plug it in. So I'm going to have dv dt, oh, I'm sorry, wait, I already know what that is. That's what I forgot to say. dv dt is 100 cubic centimeters per second. So that's going to be 100 centimeters cubed per second. Let's not do it like that. We'll just put the, at the end, we'll put the units. But make sure you put the units at the end. 100 cubic centimeters per second times 1/4, and then we're going to substitute R, we know it now, because it's when R is equal to 25. So we'll have 25 squared, and that will give us, the volume will be increasing at a rate of 1/25 pi centimeters per second. And that's going to be the rate that it's increasing. At that point, as it's getting bigger, the volume is going to be getting bigger. So the right here is where the radius is 25. It started at one point and it started getting bigger and bigger and bigger. And as that's happening, your volume is getting bigger and getting wider and not wider, but just increasing. Which, by the way, remember, if something's increasing, you're going to have a positive change. And if it's decreasing, it's going to be a negative change. And you have to put that in your formula. All right, here's another related rate problem that you'll see, and it has to do with a shadow and some kind of pole. This also could come in the form of a ladder sliding away from a building. But in this case, it's a 6-foot tall man walks away from a street light that's 21 feet tall at a rate of 3 feet per second. They want to know at what rate the length of the shadow changes when is changing when he is 8 feet from the light, and at what rate is the tip of the shadow moving when he is 10 feet from the light. So we're going to go ahead and follow the steps. The first step is draw or sketch the picture. So I have this we have this street light. And there's a man that's walking. He's 6 foot tall. And he's casting a shadow as he walks. So as we put this together, you start to notice that we have, one minute. So I have this picture of this man. He's 6 foot tall. So I want to go ahead and label it. And this is this part, write down known information. If I'm labeling it, I still think that's writing down the known information. And the light is 21 feet high. And I know that it's moving at a rate or I'm looking for, I know that there's a shadow and I'm looking for what the shadow is moving at. What is the rate that the shadow is moving? I'm also going to fill in some other information. I know that we're going to need to know it when it's 10 feet from the light. But at this point, we're going to go ahead and just label some things. I'm going to say S for shadow. And we don't know this, so we'll call it X. And this whole length, I'm going to call it Y, which is if I added the S plus the X together. that would give me y. So I'm gonna have to think of a formula. And in the last slide, I gave you some different hints to formulas that we're gonna probably be using. And I'm gonna go with, because I have this triangle, I have this triangle with the man, which really starts here. So we'll go like that. So I have this triangle with the 6 foot, and then I have this big triangle with the 21 foot. So I'm gonna go with the use similar triangles for this one. And how I'm gonna do that is, let me delete this picture, so we already decided. And I'm gonna go ahead and so it's like I see that there's similar triangles because I see what's happening. It's just like when you see a certain problem and you know right away that's gonna be a Pythagorean theorem. So I'm gonna go ahead and set up these similar triangles, and I'm gonna go, all right, with this little triangle here, S to this big triangle here, that's the bottom of the little triangle to the bottom of the little big triangle, is gonna be equal to the height of this little triangle to the height of the big triangle, because there's 2 triangles in here. And hopefully you do see them. And that's going to be 6 over 21. And then I just go ahead, and usually when you have 2 equations or 2 fractions that are set equal to each other, you just go ahead and cross multiply. That'll give me 21s is equal to, and I'm going to cross multiply here and distribute the 6 when I do it. So it's going to be 6s plus 6x. If you're not sure about that, it's just 6 times s plus x, and then I distributed it. And then I'm trying to find out what's going on here. But at what rate it's changing. So what I do is I still go ahead and I get things, I'm sorry, what's going on here? I try to move things. So since I'm trying to find out what's going on here, but at what rate it's changing, I know that I got to get that alone. So I'm going to minus 6s from both sides, and that's going to give me 15s is equal to 6x. And let's go ahead and get s alone. S is going to equal now, let's make some more room, hold on. S is going to equal now 6 over 15x, but really let's just reduce that now, and that's going to equal 2 over 5x. And then we can take ds dt. So we're going to take ds dt of 2/5 x. So that gives me, because this is ds, this is an x. So we're looking for ds dt with respect to time of 2/5 x. So I have to take whatever that is, and that's just like a constant. So when you take the derivative of this, I end up with that constant, 2/5, but I have to take the derivative here of x, dx dt. And now I can plug in, because I know we're going to do the evaluate step. It says what's going on at this right here, dx dt is 3 feet per second. So I'm going to go ahead and plug in 2/5 times 3, and that's just going to give me 6 feet, or 6/5 feet per second. That's the rate that the shadow will be moving at a rate of 2 feet per second. Okay, so we found that the length of the shadow is changing at the rate of 6 feet per second. So I did part A, but I didn't even use this. So that makes me wonder how they gave me that information. Don't I need it for something? But if you know that it's moving at a constant rate of 6 feet or 6/5 feet per second, it doesn't matter how far away from the light it's going to be, it's moving at this constant rate. So this answers that. So this part right here, we didn't even use. Did you notice that we didn't even use it? Okay, so now let's go to part B. Part B is, at what rate is the tip of his shadow moving when he is 10 feet from the light? So that's D, we're saying the position, we called it DS in our picture. Pretty sure we did. Let me just go make sure. I erased, but I'm pretty sure we did call it DS dt. And that's the shadow. So we want to know at what rate it's moving when he's 10 feet from the building. So I'm going to go ahead and think of the formula. So we already drew the picture. We know our information. We know that the length is increasing. And I do want to say one more thing. We know that since it's increasing, all our derivatives, because as you walk away, the shadow gets bigger and bigger, I think. Well, anyway, so that's why we're using positive. So keeping that in mind, we had drawn a picture. I'm just going to redraw it really quickly. And we had the man right here, and we wanted to know at what rate the tip is moving right here as you get 10 feet from the light. And so we wanted to know now, we know that we have this whole length, and that's x plus s. So I can use that, and we call that whole length y in our picture. So I know y is equal to s plus x. So I can use this formula and take the derivative of it. So that's going to be the formula that I made, and I'm going to differentiate it implicitly. Now I want to know this whole change. So that's dy dt with respect to time. And that's going to be of this whole thing. So I'm just going to go ahead and take the derivative. That's going to be the derivative of s with respect to time plus the derivative of x with respect to time. And that's just the addition property when you differentiate. And that just gives me with what I have, we found this. We found it just in part A. We found ds dt, and they gave us dx dt because it's moving at a rate of 3 feet per second. So we already know that, so that's given. So I can go ahead and plug in what we found, that was 6/5 feet per second. And this was given at 3 feet per second. And to find this, I'm going to have to change this. Let's just change this. Instead of 3, we'll put 15/5 so we can go ahead and add these two. And dy dt now ends up being 21/5, or you could put 4.2 feet per second. So you want to write these out in a sentence in words. You want to write, the tip of the shadow is moving at 4.2 feet per second when it is 10 feet from the light. Of course, it's a constant rate, so the same thing goes with the 10 feet. So you might want to write it down. I'll make some room. So you want to write it down as the tip of the shadow is moving at a rate, and is moving at a rate of 4.2 feet per second. And that's how you would write it in words, because you know that they want you to write things in words. And make sure you learn how to write those. So those are the two examples that I'm giving today on related rates. And next week, we'll go ahead and do 2 different examples. If you have any questions, please contact your teacher, and be awesome.